And here's a multiple choice question that we're asking that really questions the student about some other things as well. But it says the environmental impacts of cutting down a forest to obtain wood as fuel for heating and cooking could include, and so in a way this is a kind of system analysis that's talking about how you're obtaining the fuel and then what you're doing with that fuel when you try to harness the energy in it. You release particulate matter into the air. And in this case, really this is not identifying the incorrect part of this answer, part 3, is that it doesn't lead to a large rise in sulfur dioxide. There's little or almost no sulfur dioxide coming out of wood combustion. That would be correct if, say, we were talking about coal or oil production. But for that reason, D, Roman numeral 1 and 2, would be the best choice to choose in this question. Here's another one, and I don't know if you want to go through all of it, but everybody gets very excited about fuel cells and how efficient certain aspects of having an electric car powered by hydrogen is. And that's really true. An electric motor is about 80% efficient. So an electric automobile is not quite 80% efficient, but I think it would be safe to generalize and call it that. So how do you get the hydrogen? That's the big question. A reformer generates hydrogen at about 50% efficiency, and generally a reformer can use various kinds of renewable energies like wind or solar, but the most common one to see today is natural gas. So you're taking natural gas to generate hydrogen at about 50% efficiency. And then the efficiency of transfer from the hydrogen to electricity in a fuel cell is about 80% efficient. And then, as I mentioned before, an electric motor is 80% efficient. So you can multiply it out, 0.5 by 0.5 by 0.8, and you would get an overall efficiency of this part of your system of 32%. How about a coal-generated electricity system to power an electric car? Well, we've already pointed out, I'm sorry, I used 0.35, 35% before, but it's roughly the same number. 0.36 times the 0.8 efficiency of the electric motor would give you 28.8%. So in fact, even though you have another transfer here, if in this case hydrogen and a fuel cell, ignoring the cost of course, would be 32% efficient versus coal-generated electricity to power an electric car, 28%. However, the story changes if you consider natural gas-powered electricity, because natural gas conversion to electricity is 55% efficient as opposed to 35 or 36%. And the story would change even more if you talked about something like hydro or solar or wind-generated electricity. So these are all things that you can look at and do systems analyses of and maybe get to some answers. And one thing that we haven't looked at, and this gets a little bit to the tar sand question that I raised at the beginning, and that is how do we get oil out of the ground and what kinds of energy is involved in that? And you may have heard the expression well-to-wheels equation. That is, how do you get the energy from the oil well all the way to the gas tank, all the way to the wheels of your car, and then utilize it? So here's the first part of this, and this is from a very old textbook, and it's one of these diagrams that shows how much energy gets used along the way. So if you had 100 joules of energy in the ground, this diagram, with various kinds of refining being the greatest loss, shows that about 20%, 19% of the energy, or 19 joules of 100 joules in the ground, is lost along the way, and to get to roughly 80 joules of energy in the gas tank. And this is a good 30 or 40 years old, this diagram, and it's not that different today. And part of the reason is while our refining has become more efficient, sometimes to the exploitation and transport, because we're going so much further to get that oil or gas or coal or the tar sands that you then are using a lot more energy to refine. So really today, the number that you see is 80 to 85% of the energy in the ground ends up to the energy in your gas tank. And then your car, depending on whether it's a hybrid or an internal combustion or an electric vehicle, well, it wouldn't be electric with gasoline, but you then have to talk about that conversion. So this is a long way, and we are today a long way from, I don't think too many of our students know the reference to the Beverly Hillbillies, but this television program in the 1970s had this guy in Pennsylvania hunting squirrel, and his shotgun blast caused oil to come bubbling up out of the ground. So there was a seam of oil, the surface, an oil well right at the surface, and just breaking the surface of the ground caused the oil to come up. That's certainly not what we're doing today. So crude oil is deep, deep in the ground or under the ocean, or it's in another form and we have to convert it. And so that's why all of these things, this well-to-wheels equation, is so much more complicated than it used to be. And here's a diagram that I don't think you're going to be able to see very well. So if you can read any of these lines, could you do me a favor and raise your hand? I'm just curious if anybody can see it. Oh, okay, some people can. Great. I put the reference at the bottom so that you could look at this, because this is well-to-wheels emissions in grams of CO2 equivalent per mile driven. And this is showing the conventional internal combustion car and how much it is. So this is saying it's about 350 grams of CO2 equivalent per mile traveled. And it shows some different things like hybrid electrics, which are down at 250 or 275, and natural gas vehicles and diesel vehicles. And then it shows some different kinds of plug-in hybrids. So these are hybrid vehicles that also allow you to charge the battery and not use gasoline if you make short trips. And it breaks it down to the West Virginia grid mix, which has much more coal in the grid than the California grid. And it has a whole great deal of information that I think, especially this time of the year, your students are ready for it. So if you're still doing challenging projects in your class, or maybe save it for next year, you could take a look at this. And it's really looking at some different choices. And in this sense, this is all a life cycle assessment. This is the end product, but it involves what fuel went into the vehicle. And that's the kind of thing that I think is great to look at, because when you really get down to it, I should also say that if you go to the website, you'll see this makes a lot of assumptions about, how many miles are driven and so on. But if you get down to it, the best thing is to have the most efficient vehicle, the vehicle that gets the greatest number of miles per gallon or per energy content of the fuel, or if you're concerned about global climate change and you want to reduce CO2 concentrations, grams of CO2 equivalent per mile, you want to find the one that releases the least. And you don't really, it's not going to matter so much, is it hybrid, is it hybrid electric? It's just what is the one that's the least. So you'll see that some of the ones that are the least might be plug-in hybrid electric vehicles, but there are certainly some others that can have some pretty good numbers. Like here's a vehicle, it says cellulosic ethanol, and you have to, corn ethanol, and you have to wonder where's the corn coming from. We'll look at that in a second. So those are just some ideas to think of. And one graph I want to show you from Chapter 12 in our book that really is important when looking at this diagram is where you live it very much influences what your fuel mix looks like to generate electricity. So this is the average for the United States. About 45 or 48% of our electricity nationwide comes from coal. But as I mentioned, I live in Vermont, where it's about 40% nuclear and 40% hydroelectric, maybe 45-45. And I know some of you are in Ohio and in the central part of the United States where the fraction of coal might be higher. If you live on the East Coast or maybe on the West Coast, natural gas might be higher, and so on. So that's a really important thing to talk about if you're going to talk about a plug-in hybrid electric car. So that's a car that for short distances, maybe 10, or if you're talking about an all-electric car, if you're getting your electricity off the grid, it's really important to talk about, where's that electricity coming from?